So in this lesson, we're going to introduce a brand new type of function, but it's both new and not new at the same time. Because notice as we look at it, so here's my function f, the notation looks a little bit scary, but notice we have built into it, we have a quadratic function. We have an x squared term in here, and that is familiar to us. And then we also have a linear function. We have sort of a y equals mx plus b. So these pieces are familiar to us, and this function is called a piecewise function, and it's made out of parts that we already know. Most of the math we're doing here won't be new to us, but we're going to talk a little bit about the notation and why these things are useful to us. So this particular problem is about the lactate in my blood. While I'm riding my bike, you guys know I like to ride bikes. Blood lactate is the thing that makes your muscles like burn when you work out. So you guys have probably felt this before, maybe when you run the mile. And the reason that this applies to like a piecewise function is that your body deals with that burning feeling differently depending on how hard you're working. So I made this up, but it is based on just like what the real like lactate curve looks like. So let's look at the graph of this thing. We're going to use Desmos to do that. And we'll see why these types of functions are useful to us. So here's my graph of f. And here's, by the way, how you type these in on Desmos if you need to with little curly brackets. And notice we have this red piece that is my quadratic piece, and then my green piece that is my linear piece. So when the graph goes from red to green, so at 300 for me in this example, that's when you really start feeling like you're dying, right? So your muscles are burning, your lungs are burning. It's not a pace that you can really keep up for a long time. Whereas in that red area, when the curve is nice and flat, you can keep that pace up for a while. So that's like the pace at which you're chilling. So that might be like a walk or a light jog for some of y'all if you're running the mile. Whereas like when you get into the green, that's when you really start going hard and you really start to build up that burning feeling really quick. So then this sharp point, well, that represents when the acid really starts to build up in your muscles and you really start to feel the burn, right? So we're going to sketch this graph. It doesn't have to be perfect, but it should have this point 300. And use two colors if you can. Use one color for each piece, right? So we started a little bit less than 2, and then it kind of got short and flat. Started to climb a little bit, and then we'll switch colors, and then we'll go up steeply from that point. And that point is where our pieces meet up. So that point, take a guess what that x value is. It's 300. Okay, so that's like the sort of the maximum pace I can hold on a bike for a while. Okay, so there's our graph, and notice for x less than 300 in this case, it's my quadratic piece, right? And then for x bigger than 300, bigger than or equal to 300, it's my linear piece. And in this case, they meet up at a nice point like that. So let's see how we evaluate these two. And I did these both already in my calculator. You're free to write these down. But before we check this out, what we're going to do is just note, so f of 200 means plug in 200 for x, right? And 200, make a note, is less than 300. I notice I did it in my quadratic color. F of 400, again, means plug in x equals 400. And make yourself this note, 400 is greater than or equal to 300. So that is, again, in my linear color. I picked those colors on purpose. Because as I look at my calculator, notice what I did differently. You can probably guess. So to evaluate 200, I plugged it in for x in my top piece, though, right? So you can write this down in this box in your notes if you need to. But f of 200 is equal to 1.504 because I do 200 minus 180 squared over 100,000 plus 1.5. F of 400, notice what I did differently, right? So I've plugged in 400 for x here, but I plugged it into the linear piece, right? And that makes sense because 400 is bigger than 300 at 5.35. So that's how we work with this notation. These inequalities are sometimes called the bounds, and they tell us which x to use, right? Or tell us which piece to use for which x. So you can take a second now and pause and write down these expressions that I typed into my calculator in each box, if you feel like that might be helpful to you if you're not going to remember how to do these. Okay, once you got that, we're going to take a look at one more example where piecewise function might be useful to us. So take a second and read example 2. This is a really common situation, right? So we have a $4 charge for the first hour, and then $2 per hour after that. It's a parking problem. So parking garages never really charge like linearly, right? It's not like they charge you like $1.50 for being there an hour and a half, right? They charge you $1 for the first hour, $2 for the second hour. So rather than getting a nice smooth curve like this, really we're going to get pieces, steps really. It's called a step function. So let's see what this particular step function looks like. So $4 for the first hour, that means we're going to have a little chunk here, right? Then $2 per hour after that, up to a daily maximum of $10. Okay, well, that means for my second hour, it cost me $6. For my third hour, it cost me $8. And for every hour after that, it cost me $10. And draw a little arrow there because that's my daily maximum. So that's the most they're going to charge me, which is nice. So there's my function. Here's how I would write that out. So f of x equals, and then I'm going to leave a little bit of space because I'm going to make a bracket here, but I'm going to say equals 4 for, and you can write the word for if you want. I like to. 0 less than, it just makes the notation a little bit clear, less than x, less than 1, right? So that's my first hour. Then 6, well, that's for x is bigger than 1, but less than or equal to 2. And notice I picked these inequalities for a specific reason. So when I've parked exactly 1 hour, I'm paying $4, not $6. And when I've parked just a little bit more than 1 hour, up until exactly 2 hours, I'm paying $6. That's just based on the text. $8 for my next piece, and then $10 for my last piece. And my last piece is whenever x is greater than 3. And here's my nice curly bracket. It's easier to draw that afterwards. So there's a piecewise function to represent our situation. Okay, so I have a problem with this graph that we're going to fix before we move on. So notice it's unclear based on my graph whether this point or this point. In fact, the way I drew it, it's not really a function, right? Because this x equals 1, it's not clear which y it goes with, right? So I'm going to make that a little bit more clear by using a closed circle and an open circle, right? So the closed circle is on the piece that we want to evaluate at x equals 1. The open circle is the piece we want to leave out. Same thing here, closed circle, open circle, and then closed circle, open circle. And notice these correlate rather with the bounds, right? So a plain old greater than is open, and greater than or equal to is closed. Okay, so notice these came out quite different, and they're different for a lot of reasons. But the difference I want to talk about between the two is called continuity. So we have continuous versus discontinuous functions. And these are really exactly what it sounds like, continuous and discontinuous. So if you have a good vocabulary, your guess is probably good. So continuous means, in this case, you can draw it without picking up your pencil. And that was, of course, example 1 was continuous. Discontinuous means, well, you can't do that. And that's example 2. So that's one of the reasons why these things are useful to us, is they allow us to model things like our parking garage. A lot of things we run into in real life are not continuous.